Good morning, good morning, good morning. It is my pleasure to welcome you to the Kavli session entitled Exploring the Cosmos, one of the signature events at the APS Global Physics Summit. And so I'd like to start by extending some very special thanks to the Kavli Foundation for making it possible. Thank you. So this session is a celebration of breakthroughs that expand our understanding of the universe. And it's especially fitting to hold this session at the start of the International Year of Quantum Science and Technology, because it now seems that the universe itself was born from a quantum fluctuation. How mind-blowing is that? So for those who don't yet know, IYQ is a year-long initiative led by the APS and designated by the United Nations to mark the 100th anniversary of Heisenberg's famous paper on quantum mechanics, but also, and perhaps more importantly, to celebrate the profound impact of quantum science on research, technology, and society. And so the International Year was launched by UNESCO last month in Paris, and this video was prepared for the launch. Let's take a look. So I hope you too are inspired by quantum science, and I encourage you to contribute your time and talent to this global effort. Now, I also want to just take a minute to acknowledge that many of you are concerned about the events unfolding in Washington. I want you to know that APS is working across multiple fronts, and I encourage you to visit the APS Government Affairs booth in the APS Village to learn more and get involved. And in addition, there'll also be a special town hall tomorrow at 10:45 in the morning with APS President John Doyle. You'll hear about our efforts to ensure that science and physics stay a priority. Now, our speakers here today will take us through some of the most exciting frontiers in astrophysics, cosmology, and fundamental physics. Their work inspires us to ask bold questions, to challenge assumptions, and to seek even deeper connections between the smallest quantum scales and the greatest cosmic phenomena. Therefore, it is my honor to introduce our session chair, Professor David Garfinkel. Dr. Garfinkel is a distinguished professor of physics at Oakland University and serves as co-chair of the Global Physics Summit. His work on gravitational physics and numerical relativity has heightened our understanding of the cosmos, and he will be guiding us through today's discussions. David, the floor is yours. Thank you.
Thanks very much. Welcome to the Kavli session. I want to start by saying that when you go home, your friends, relatives, and neighbors are all going to ask you, what cool new physics results did you learn about at this conference? And you are going to answer with reference to the results of this session. Now, to a large extent, progress in astrophysics, cosmology, and gravitational physics is driven by instruments and the people who design them, build them, run them, and analyze the data. In the 3 talks that you're going to hear today, you're going to learn about 4 of these instruments. The first, NANOGrav, is basically a collection of radio telescopes using pulsar timing to detect gravitational waves. In the second talk, you'll learn about the dark energy spectroscopic instrument, which maps out the cosmos on the largest scale. And then in the last talk, you're going to learn about 2 instruments for measuring the cosmic microwave background, an older one, ACT, and a brand new one, the Simons Observatory. And what we hope to have today is both a picture of how these wonderful measurements are done and also some exciting results of the things that they've found. So our first speaker is Sarah Vigeland. And Sarah got her undergraduate degree at Carleton College and then her doctorate at MIT. And she is now a professor at the University of Wisconsin-Milwaukee. And she has looked at gravitational waves, starting with the relative high frequency waves that were detected by LIGO, but now moving on to the much lower frequency waves that have just been detected by NANOGrav. So let's see. Sarah, can you come up and begin your talk?
Okay, can you all hear me okay? All right. Okay. All right, well, good morning. I want to begin by thanking the organizers for inviting me and giving me this opportunity to talk to you all today on behalf of the NANOGrav collaboration. The last couple of years have been very exciting for us in NANOGrav and for the entire pulsar timing array community. In June of 2023, we and our international colleagues published the first evidence of a gravitational wave background at nanohertz frequencies. This is a major milestone for us as a field. And today I'm going to talk about where we go from here. What can we learn about physics and astrophysics by observing low frequency gravitational waves? Astrophysical and cosmological sources are emitting gravitational waves over many orders of magnitude in frequency. And just as we need different kinds of telescopes to observe the entire electromagnetic spectrum, we need different kinds of gravitational wave detectors in order to observe the entire gravitational wave spectrum. LIGO and other ground-based interferometers are sensitive to high-frequency gravitational waves. And since the first detection in 2015, they've observed hundreds of gravitational wave events from the mergers of stellar mass compact binaries. As we go to lower frequencies, you're talking about sources where the masses are larger, the orbital separations are bigger, or both. LISA and other space-based gravitational wave interferometers will be sensitive to millihertz gravitational waves, and we expect to find a wide range of sources there, everything from compact binaries in our own galaxy to merging massive black holes in distant galaxies. Both of these detectors use laser interferometry to detect the stretching and squeezing of space-time. But if we want to go to even lower frequencies, nanohertz, we need a completely different method. Now, nature was very kind to us by providing us with pulsars, which can be timed to tens of nanoseconds over decades timescales, and that makes them ideal for measuring long period gravitational waves. There are a number of pulsar timing array experiments around the world right now. I'm a member of NANOGrav, which stands for the North American Nanohertz Observatory for Gravitational Waves. For most of our history, we primarily used the Arecibo Observatory and the Green Bank Telescope to observe our pulsars. Unfortunately, Arecibo is no longer operational. So right now we're observing with Green Bank, the Very Large Array in New Mexico, and CHIME in Canada. And we're joined in our efforts by our colleagues in the European Pulsar Timing Array, the Chinese Pulsar Timing Array, the Parkes Pulsar Timing Array, the Indian Pulsar Timing Array, and the Meerkat Pulsar Timing Array. And all of these groups also collaborate as the International Pulsar Timing Array, or IPTA. Over the past couple of years, all of these groups have published independent analyses of their data sets and found evidence of a gravitational wave background. So what's shown here are the results from each group, the measured interpulsar correlations, which match the prediction for a gravitational wave background. Okay. This is a very exciting moment for us and is the first evidence of nanohertz gravitational waves. Now, pulsars are rapidly rotating neutron stars, and as they rotate, a beam of radio waves sweeps around like the beam of a lighthouse. And what we see with our radio telescopes is a series of pulses that can be timed very precisely. When we time these, we learn all about the properties of the pulsars themselves, but we can also search for an additional delay, a redshift induced by gravitational waves, and that redshift is given by the expression there. So the delta Hij, that's the gravitational wave. That's where all of the information about the source lives. And the term out front is basically describing the relative position between your pulsar and your gravitational wave source. Now, we don't just use a single pulsar because there are lots of things that can affect when these pulses arrive on Earth. We use an array of pulsars because we're looking for something that affects all of the pulsars in a particular way. Now, if you don't have a single source, but you have a whole population of sources, you can add up the effect from all of your individual binaries scattered throughout the universe. And what you find is that you're going to get a signal that's correlated between two different pulsars. And the correlation is going to depend on the angular separation between them. So it's maximum if the two pulsars are close together on the sky. As you move the pulsars apart to about 90 degrees, the signal becomes anti-correlated. And as you move them even further apart, it becomes correlated again, but not as correlated as if they were in the same direction. So this is known as the Hellings and Downs curve, and it's the signature of gravitational waves. It's how we know that what we're seeing is gravitational waves and not some other effect. So by observing a whole array of pulsars, we can measure the interpulsar correlations at a range of angular separations and search for this pattern. And what I'm showing here are the reconstructed interpulsar correlations from the NANOGrav 15-year data set. So the blue violins are the measured correlations, binned in angular separation. And then the black dashed line is the Hellings and Downs curve. And you can see that they agree very nicely. The false alarm probability of this signal is 10 to the minus 3. Now that we have seen nanohertz gravitational waves, what can we do with that? How can we use that to learn more about physics and astrophysics? There are a number of major questions going forward that we can hope to address. The first one is, what is the source of the gravitational wave background? Is it supermassive binary black holes or something cosmological? It's possible that many different sources are contributing to this background. And if that's the case, is there a way we can disentangle these contributions? Can we, for example, subtract off the component from supermassive binary black holes and see gravitational waves from inflation underneath? What can we learn about supermassive black holes and galaxy evolution from these observations? The signal that we see can help us learn about the properties of the black holes, their masses, the environments around them, as well as help us study galaxy evolution. And finally, what can we learn about fundamental physics? What kind of constraints can we put on alternative theories of gravity? And how can we constrain new physics and cosmology? The possibility that we could see gravitational waves from some kind of cosmological source in the early universe is particularly exciting because with gravitational waves, you can peer back to earlier in the universe's history than you can with light. With light, you can only look back as far as the cosmic microwave background. With gravitational waves, in theory, you should be able to look back to a tiny fraction of a second after the Big Bang and really see what was happening in the universe right when it started. Now, unfortunately, I don't have time to talk about all of these in a lot of detail, so I'm just going to touch upon them. But there is a talk in the next session by Paul Baker where he's going to talk more about what we can learn from pulsar timing arrays. I'm going to start with what we can learn about gravity itself. So the prediction that gravitational waves should induce Hellings and Downs correlations is connected to the gravitational wave polarizations. In general relativity, there are only two polarizations, the plus and the cross. But in more generic theories of gravity, you can have up to 6. So there are 4 polarizations that are not allowed in GR that could be present in some other theories of gravity. And all of those polarizations will also induce a common signal in your pulsars, and it will be correlated, but the correlations will be different from Hellings and Downs. So what I'm showing here in the plot is a comparison between the correlations induced by a scalar transverse mode and the Hellings and Downs curve. And the scalar transverse mode is the blue, it's the blue polarization in the diagram on the left. Okay. So by measuring the interpulsar correlations very precisely, we can search for deviations from Hellings and Downs that could be caused by some alternative polarizations. In the absence of those deviations, we can put constraints on how much power might be in these additional modes. Now let me talk about the sources. We know that massive galaxies like our own have supermassive black holes at the centers. And we know that galaxies grow and evolve through a series of mergers. When two massive galaxies merge, their black holes will come together and form a binary. Now, exactly how long this takes is still an open question because it depends on the environments around them. If there were no matter around the black holes, it would actually take longer than the Hubble time for the black holes to form a close binary. Now, we know that astrophysical black holes are not in vacuum, though. They're surrounded by stuff. They're surrounded by stars and gas. And the presence of the stars and gas causes the orbital decay to accelerate, bringing the two together. Once they reach subparsec separations, that's when they're observable by pulsar timing arrays. They're orbiting, the orbital periods are maybe months up to decades. The orbit is evolving very slowly compared to a human lifespan, though. And so we often refer to these as continuous waves because over the time span of our experiment, or even our lives, these black holes are basically hanging out at some constant orbital separation. They will, though, eventually merge and form a single black hole. And we see that familiar in-spiral merger ring-down waveform that we've seen so many times from LIGO. For most sources, this is going to happen at higher frequencies than what pulsar timing arrays can observe. But for some of them, the signal may be observable by LISA. So all of the supermassive binary black holes in the universe are emitting these gravitational waves. They're not evolving significantly when they're in the nanohertz. If they're circular binaries, they're emitting at just a single gravitational wave frequency, so kind of like a single note. And when you combine all of these together, when you add up the gravitational waves produced by all the supermassive binary black holes in the universe, you get the gravitational wave background, kind of a hum of gravitational waves. Now, the properties of the gravitational wave background depend very strongly on the population of black holes. And what's shown here are some sample gravitational wave background spectra. Now, broadly speaking, the amplitude is most sensitive to the masses of the black holes. So if the black holes are more massive, the signal will be stronger. And it's also sensitive to things like the galaxy number density and the galaxy merger rate. So basically, how many binaries are there? The shape of the spectrum tells you about the physical mechanisms causing the black holes' orbits to evolve. Is it just gravitational wave emission? Or at low frequencies, are these black holes coupled to their environments? If so, you're going to get a turnover in the spectrum where the spectrum depletes at really low frequencies. That's because at low frequencies or large orbital separations, the black holes will be evolving faster, so they hang out at those separations for less time, so there's a weaker signal. So this is a reconstruction of the gravitational wave background spectrum from the NANOGrav 15-year data set. We see that it extends across the lowest frequencies from 2 up to about 28 nanohertz. It's broadly consistent with what we expect for a population of supermassive binary black holes. On average, if you have a population of supermassive binary black holes that are circular and evolving only due to gravitational wave emission, you get the dashed black line, so it follows just a power law. So what we're seeing is broadly consistent with that, but right now our ability to characterize the spectrum is still a bit fuzzy. With longer observation times with more pulsars, we'll be able to make more precise measurements. Right now, what we can say is the following. We can say that what we're seeing is consistent with black holes. There is some preference for models that include environmental interactions over models that only include gravitational wave emission. So it's possible we're starting to see that at the lowest frequencies, the black holes are interacting with their environments. The overall amplitude of the signal is high. It's on the higher range of what people were expecting. And that's pretty interesting because that means that a number of things might be a bit higher than we had anticipated. Things like the masses of black holes, the rate of galaxy mergers, the efficiency of binary in-spiral. Maybe all of these are a little bit higher than anticipated. Maybe one of them is much higher than anticipated. With more data, we'll be able to measure all of these properties a lot more precisely, and then we can compare against what we've inferred from electromagnetic observations. But there are a number of other potential sources of nanohertz gravitational waves. What's shown here are a number of different models. The top panel is models related to inflation, the bottom topological defects, and the colored lines are the different possible spectra. The black shaded regions show the NANOGrav results. Our results are broadly consistent with all of these except for stable cosmic strings, which are disfavored. So right now we're not able to, we don't have strong evidence for any of these models over each other or over supermassive binary black holes. It'll take more data to really be able to distinguish between them. Now, the reason it's plotted like this, spanning over so many orders of magnitude and frequency, is that for some of these sources, they're predicted to emit gravitational waves across the gravitational wave spectrum. So in the future, we'll be able to combine observations made by pulsar timing arrays, LISA, and future ground-based gravitational wave detectors to better constrain these possible sources. In the coming years, one of the most important questions we aim to answer is, what is the source of the gravitational wave background? And if it is coming from supermassive binary black holes, there are a couple of things we can look for. If it's supermassive binary black holes, then the signal is coming from the sum of gravitational waves emitted by a finite number of individual sources. And so then there's two things you can look for. The first is some amount of anisotropy. the signal is not going to be perfectly uniform across the sky. The other thing you can look for is features in the spectrum. So at some frequencies, there may be a little bit of extra power because maybe there's a particularly massive nearby binary that's dominating the spectrum at that frequency. We can look for both of these things. If we see them, that's evidence for the black hole hypothesis. If we never see them, that's evidence against the black hole hypothesis. Based on simulations of how much anisotropy we expect, we think that with about 20 years of NANOGrav data, we should start seeing anisotropy. Now, when we'll be able to find some of these spectral features kind of depends on where are those most massive binaries? Are they close by? Is nature going to be kind to us or not? We should be able, though, to resolve a handful of individual sources and separate them out from the gravitational wave background. And that opens up the possibility of doing multi-messenger astrophysics of individual sources, combining gravitational wave observations with electromagnetic observations. If our individual source is interacting with its environment, say it's got an accretion disk surrounding it, then we may be able to see it as an AGN and look for features in the AGN caused by the binary motion. Right now, there are a lot of candidate binaries that have been identified by looking for things like variability in AGN light curves or spectral features. But they haven't been confirmed as binaries. And that's something that pulsar timing arrays can do. We can do targeted searches for gravitational waves from these sources and either confirm them as binaries or put constraints on their properties. Now, even if our individual source isn't interacting with its environment, we can still do multi-messenger astrophysics because we know that it's going to live inside a galaxy and that galaxy would have undergone a recent merger. Now, gravitational waves in general are notoriously bad at localizing things on the sky. Pulsar timing arrays are no different. So we expect that our individual sources initially will have very large sky localization regions. There's going to be a lot of potential galaxies. So we'll have to make cuts based on the galaxy's mass and distance to narrow it down. And then we can do follow-up and try to identify the host galaxy. Maybe we'll be able to tell that it's undergone a recent merger because, for example, maybe there's an increase in the star formation rate. One piece of good news is that as the significance of the signal increases, the sky localization region should continuously decrease. And that means that with more time, we'll be able to localize it better. We'll be able to identify that host galaxy. Okay. So let me wrap up by talking a little bit about where we are now. Right. So right now within NANOGrav, we are putting together the next NANOGrav data set. The next NANOGrav data set is going to have 77 pulsars observed for up to 20 years. And this is going to be the first NANOGrav data set that contains data, that contains observations made with CHIME in Canada. We're also working with our partners in the IPTA to put together IPTA DR3. So this data set is going to contain observations made with all of the telescopes indicated here, and I've highlighted the ones that will be part of the IPTA data set for the first time, because I want to emphasize just how much new data are going into this data set. A number of these telescopes are really brand new, and the sensitivity that we're getting with some of them, like FAST in China or Meerkat in South Africa, is really astonishing. The full data set is going to contain observations of 121 pulsars with a total baseline of 25 years. Now, roughly speaking, you can say that the sensitivity or the significance of the correlation scales linearly with the number of pulsars. For comparison, the NANOGrav 15-year data set has 67 pulsars. We're going to have almost twice as many in IPTA DR3. So we expect that the significance of the correlations will increase a lot. So in conclusion, NANOGrav and other pulsar timing array collaborations around the world have found evidence for a gravitational wave background at nanohertz frequencies, opening up a new window on the gravitational wave universe, the low frequency end of the spectrum. Now, in this part of the spectrum, we're seeing completely different sources than those that are seen by LIGO. We think that the signal is likely coming from a population of supermassive binary black holes, but it could also be coming from a number of cosmological sources produced in the early universe. With longer pulsar timing baselines and more pulsars, we'll be able to better measure the spectrum of the gravitational wave background, and we'll be able to better measure the interpulsar correlations. Better measurement of the spectrum will help us determine the source of the gravitational wave background and learn about its properties, things like the masses of black holes, the galaxy merger rate, etc. Better measurement of the correlations is how we are able to measure the gravitational wave polarizations and do tests of gravity. It's a little hard for me to believe that it's already been 10 years since gravitational wave astronomy began. Sometimes it feels like it was only yesterday. And in those 10 years, we've learned so much about compact objects, stellar evolution, and gravity from the observations made by LIGO. I think the next 10 years are going to be just as exciting, if not more. And I look forward to the 2035 APS meeting when we can all hear about everything we've learned by observing nanohertz gravitational waves. Thank you.
Very much for that excellent talk. We have plenty of time for questions. So what I'd like to do is to have people go to the microphones to ask the questions, and I will call on you. I will either say to my right or to my left, and then come up to the microphone and ask your questions. And can we have those spotlights down a little bit so I can see people at the microphones?
Thank you for this excellent talk. Is the time scale for the sensitivity to for the discriminating power between different models set by the number of telescopes or set by the physics process? What would decrease that time, or is that not possible?
Sorry, you're talking about discriminating between black holes and cosmological sources, or
any of them?
Any of those. Okay. So for discriminating between black holes and cosmological sources, I think anisotropy is really key. And our sensitivity to anisotropy depends a lot on the number of pulsars. You want to have as much sky coverage as possible. So adding more pulsars really helps you out with that. In terms of distinguishing between different cosmological models by looking at, say, the shape of the spectrum, that's going to be very tricky. And I think it's actually, we still have to kind of figure out whether it's better to target the high frequency part of our spectrum versus the low frequency part. Increasing sensitivity at the low frequency end requires just waiting for longer, right? So you're able to observe waves with longer periods. At the high frequency end, the sensitivity is really set by the amount of white noise in your pulsars. So by building larger telescopes, you can decrease the radiometer noise. You can measure the high frequency part of the spectrum a lot better.
Okay, on my left.
Hi, thank you for the talk. I noticed in one of the waveforms you showed earlier, there was memory.
Yes.
Is it possible to detect memory with PTAs, and how would that manifest in data?
That's a great question. So gravitational wave memory is this kind of DC offset that happens at the end of the merger. And what it looks like in a PTA is it looks like all of your pulsars started spinning at a different rate all at the same time. Okay. Now, the rate of memory events from supermassive binary black hole mergers is unfortunately not very promising. There's a paper by a former UWM graduate student, Christina Islow, that calculates this rate, and it's not great, honestly. But memory is a generic prediction of GR, and so we do searches for gravitational wave memory. We may get lucky and be able to find one of these events.
Thank you.
So just a note for people who know me, I did not plant that last questioner in the audience. Next question on my right, please. Oh, maybe not. Sorry. On the left then.
Hi, thank you. So I was going to ask about, so the anisotropies in the gravitational wave background, are those expected to be more significant deviations than what we see in the CMB? And related to that, is there a way to use the anisotropies in the CMB to sort of infer where we might see them in the gravitational wave background?
Oh, that's a really great question. So the anisotropy we expect to see in PTAs is going to be a little different from what we see in the CMB, where you see anisotropy on all these different scales. For PTAs, we expect it's going to be basically a hotspot. Okay. As for whether it's connected to the anisotropy in the CMB, I mean, I suppose it is on some level, but I think it would be very difficult to extrapolate. But what you could do is look to try to connect that with like large scale structure. PTAs are seeing gravitational waves from binaries in the whole universe, but it's really dominated by the local universe, redshift less than 1.
Right. Okay. Thank you.
Let's see, other questions? I can't see if there's anyone at the mic. Yeah, okay, go ahead.
All right, I'll ask a question. So once you are able to find specific sources, do you gain information by subtracting them out? So if you could potentially find all the local sources and subtract them out, would that give you better information about the primordial sources?
Oh, that's a great question. Actually, can I like go backwards with these slides or?
Yeah.
Oh, okay. Sorry. There's a red button and I wasn't sure what it did, so I was afraid to click it, but it seems to be going backwards. Okay. So this plot on the right, is the answer to your question. So basically this plot on the right is showing a gravitational wave background that's made by simulating a population of supermassive binary black holes and then adding up all the gravitational waves. The purple dots are the total signal. And then the other colors are what happens if you subtract off the loudest sources, right? So what you see is that as you subtract them off, the signal becomes smoother. It follows more of a smooth curve, but it's also depleting a lot, especially at the highest frequencies. So the answer to your question, I think, is yes. If you can resolve some of these signals and just subtract them off, especially at high frequencies, it may be possible to see see gravitational waves from some other source.
Okay, with that, let's thank our speaker again. Let's have our next speaker come up. Okay, so our next speaker is going to tell us about the dark energy spectroscopic instrument. She is Nathalie Palanque-Delabrouille. She has an undergraduate degree from Telecom Paris and a PhD from University of Chicago. She works at the Institute for Research into the Fundamental Laws of the Universe at CEA Saclay. She has a number of honors and distinctions, including the Lavoisier Prize from the French Ministry of Foreign Affairs, the Prize of Excellence in Teaching of Undergraduates in the University of Chicago, the Saint-Gobain Prize from the French Physical Society, the Thibault Prize from the Academy of Sciences, Belles-Lettres and Arts of Lyon, the Astronomy Book Prize, the Irène Joliot-Curie Prize. She is a Chevalier of the Légion d'honneur, and perhaps most impressive, has been elected to the French Academy of Sciences. So please begin.
Thank you very much. I want to say that I'm now at Berkeley Lab, where I am the physics division director. So I'm no longer.
Sorry about that. Times.
Anyway, it's really, I want to thank the organizers as well. And I'm really very honored to be here today and to be presenting the dark energy spectroscopic instrument. So let me start out by giving the general context. Over the last decades, we've slowly established what is now commonly known as the standard model of cosmology. In brief, the history of the universe starts out with this hypothetical period of exponential inflation, after which the expansion continues, but at a much slower rate. After 380,000 years, the temperature of the universe has dropped sufficiently that the photons are now free to propagate, and they're giving us this first image, the first light of the universe. And the matter on its end is able to start to cluster and form the cosmic web that we observe today. In the last 20 years, we've realized that the expansion of the universe is accelerating, and this is a very interesting effect that we've discovered and that leads to the study of dark energy today. So all the physics we know and the standard cosmological model actually is able to reproduce very precisely pretty much all the observations that we've had in the last 20 years. However, it is based on two main components of unknown nature. About 25% of the universe is made of dark matter that is necessary to explain the formation of the galaxies and, for instance, the flat rotation curves of spiral galaxies, but is of unknown nature. And even more importantly, 70% of the universe, so the bulk of the energy content of the universe, is made of this dark energy component that is responsible for the accelerated expansion that we observe today, and who's also of totally unknown nature. And understanding what dark energy is really what the dark energy spectroscopic instrument, DESI, has been set out to do. So dark energy is a generic name, but what does it encompass? It's what we describe for the accelerated expansion of the universe. So there are various ways that we can interpret this accelerated expansion. On the one hand, it can come from the geometry side of Einstein's equation, which is the equation you have on the top of the slide. And in that case, it could be interpreted as a simple cosmological constant that is added into the equation, is actually the historical way that Einstein had introduced this constant in order to account for a steady state universe. On the other hand, we can also try to explain the accelerated expansion by looking at the right-hand side of this equation, which is the energy content of the universe. And then we can add another fluid in this distribution of matter and energy in the universe, which we describe through its equation of state, W, which relates the pressure to the density of this component. And a third way to try to interpret this accelerated expansion is to try to develop models beyond general relativity and to look for modified gravity to, again, explain the observations that we have today. What DESI is using, the probe that DESI is using to study the expansion of the universe and therefore dark energy, is baryon acoustic oscillations, which has been shown to be a very powerful probe. So what are these baryon acoustic oscillations, or BAOs? They arise from the propagation of baryon photon overdensity sound waves in the primordial plasma, which continue propagating until the universe has achieved a temperature that is low enough for this plasma to disappear and the protons and electrons to combine into neutral hydrogen. And so then the sound waves that had been propagated stall, and we're left with, around each regional overdensity, a sphere of excess of matter where the baryons have been carried over by the photons in the propagation of these sound waves. And so the size, the radius of this sphere is perfectly determined by the duration of the existence of this plasma, so 380,000 years, times the velocity at which the sound waves propagated. And so today, this excess of density is expected to appear with a radius of about 150 megaparsec today. And thereafter, once these sound waves have stalled, this feature of BAOs only vary with the expansion of the universe. And because galaxies tend to form where we have an excess of matter, we expect to be able to detect in the distribution of galaxies in the universe today this very specific feature. And because it has only evolved under the expansion of the universe, it means that by measuring the size of this feature at different times in the history of the universe, then we're able to constrain the way the expansion has happened over the history of the universe, and therefore the rate of the cosmic expansion. What we see in this blue map on the left-hand side is actually data from the first year of the DESI observations. Each dot in this map is a different galaxy, and we can clearly see very well this cosmic web that I've mentioned, made of filaments and voids in the distribution of galaxies today. And I've superposed on top of this map the size of the BAO feature that we're expecting to see. And it's not visible by eye, but we can recover it statistically by computing what is called the correlation function of galaxies as a function of distance, which is no less than the probability of finding two galaxies at a given separation in the universe. And the peak that you see in this correlation function corresponding to that size of 150 megaparsec is precisely the signature of that BAO feature. So it's a 3D feature, so we can observe it in two ways. We can observe it across the line of sight, in which case what we observe is an angle and which relates to the so-called angular diameter distance. But we can also observe it along the line of sight, in which case what we observe is this feature in redshift space, and then it's directly related to the expansion rate of the universe at that redshift. And so these two parameters, dm and h, encode the expansion history of the universe. And this is the raw measurement that we're doing with DESI. So far, I've only been talking about that BAO scale, so that specific characteristic feature of known size, but DESI is not measuring the clustering at a single size. It's measuring clustering over all scales that are available. And so we can get additional information from this clustering on all scale due to the fact that the redshift that we're measuring is the composition of two contributions. It's the cosmological redshift, so the Hubble expansion, on top of which we also have a contribution coming from the peculiar velocities of galaxies, which tend to fall into the densest potential wells. And so that additional contribution is actually telling us about how gravity has made the structures that we see today and how gravity has impacted the velocities of the galaxies. And so the power spectrum that you see on the top right of this slide illustrates what we can measure by studying clustering on all scales. In the monopole, you do see very clearly the wiggles that are coming from the power spectrum of the BAO feature that I mentioned so far. But you also see that we have a quadrupole in this power spectrum, which is non-zero precisely because of the effect of the peculiar velocities of galaxies. And so the study of this quadrupole actually provides additional information beyond the study of the expansion rate that we have through BAO, and provides us with information on the way the structures have grown under the impact of gravity, and also allows us to test general relativity directly. So let me now turn to what DESI is. And let me start by thanking our sponsors and all the participating institutions who are collaborating in this project. It's a very large project. We have over 900 scientists contributing. And out of the 72 institutions, roughly half of them are in the US and the other half from many countries all over the world. What DESI has been set out to do is to study the expansion rate of the universe over basically its entire history from today out to 12 billion years in the past. And to do so, we're building this huge 3D map of the universe. So 2D is easy. It's taking a photo, but to get the third dimension, we need to get the spectra, so the redshifts of the selected sources. And here in this slide, I'm illustrating the various sources that we're using throughout the history of the universe to build this 3D map. So in the nearby universe, we're using very bright galaxies that are so bright that we can actually measure the spectrum even when the moon is up. And then as we go further and further away, we use luminous red galaxies, which are also extremely bright and fairly nearby, out to about a redshift of 1. Then we have to switch to fainter galaxies, the emission line galaxies, but which happen to have in their spectra a very bright emission line because they're star forming. And this emission line is actually very characteristic and allows us not only to assess that the galaxy is of the type that we're looking for, but also is useful to determine the redshift of those galaxies. And then in the most distant universe, we're using the brightest objects, the quasars, and so these active galactic nuclei that we just heard about, and which are the brightest objects in the universe, and therefore that can be seen out to very large distances. They're not very abundant, however, so we are using them as direct tracers only out to about a redshift of 2, beyond which we're using the fact that they're extremely bright and they're used as background lighthouses to illuminate the intergalactic medium along the line of sight. And so for these farthest quasars, what we use is their light as this background information. And in the spectrum of the quasar, we actually use the information of the absorption by the intergalactic medium along the line of sight. And so on the left, you have a spectrum of a quasar as if it were observed nearby, no absorption. The largest peak is the emission line from the Lyman alpha emission, Lyman alpha transition of the quasar itself. And bluewards of that emission peak, you see the absorption of by that same electronic transition of Lyman alpha, but this time coming from the neutral hydrogen along the line of sight. And so all these series of absorption by these hydrogen clouds along the line of sight produces the Lyman alpha forest, which is the proxy that we're using to study the density of matter along the line of sight for redshifts beyond 2 and out to about 4 and above. And on the right-hand side, you have an actual spectrum that is measured, and you do see this really very dense forest of absorption lines that we're using to study the intergalactic medium. The dark energy spectroscopic instrument is using the Mayall telescope in the Kitt Peak Observatory. The 4-meter mirror is the original mirror from that instrument, but everything else has been refurbished for the purpose of this project. In particular, we've rebuilt the corrector to allow for 7 square degree field of view, so a large field of view. And then the light goes to the focal plane, which is an amazing technical development that the collaboration has achieved. This focal plane consists of 5,000 very tiny robots that each carry a fiber that they can locate to the exact position of where the galaxy is, the light of the galaxy is falling on the focal plane. And it positions these fibers to within a few microns in less than 2 minutes, which is a huge improvement compared to the previous generation of spectroscopic instruments. And this animation here is, well, actually a movie showing the dance of these robots as they're positioning to the location on the focal plane of the light of the galaxies. And then the light from the focal plane trickles down about 40 meters to a clean room where we have 10 spectrographs where we're actually measuring the spectra of the galaxies that we're studying. And so let me now switch to describing the results that we've obtained in 2024 with the first year of observation from DESI. The map that I'm showing here is the map of this footprint from the first year of observations. The reddest spots are where we have the most measurement, and the white regions are the footprint which we haven't covered yet. We have one large footprint on the North Galactic Cap and another one on the South Galactic Cap. And then with the first year of data, we mostly covered the equatorial region in the North Galactic Cap. With just 1 year of data, we already gathered more than studied 6 million galaxies, which is already 3 times as many galaxies as the whole history of spectroscopic surveys before DESI, and also studied over 400,000 Lyman alpha forests, which is also twice as many forests than all of SDSS in about 2 decades. So DESI is really an amazing redshift factory. All this data will be described in a session later today at 1:30. We are releasing this first year of spectra today at 1:30 p.m. We have the special session, and we're actually releasing all the 18 million spectra that we've observed during commissioning of the instrument and the first year of data set, even though the analysis covers only a fraction of these data. So I encourage you to attend the special session today to hear more about this data release. I mentioned that DESI is measuring 2 information, basically. Across the line of sight, we're sensitive to the angular diameter distance, and along the line of sight to the Hubble factor h of z. We can combine these 2 informations and obtain an isotropic measurement of the BAO feature. And that is what is illustrated on the left-hand side as a function of redshift or look-back time. We have 4 different classes of tracers, but in some cases, the luminous red galaxies and the emission line galaxies, we have sufficient number of tracers that we can actually even split their number into several slices in time or in redshift. And so we have a total of 7 different measurements that we obtain with DESI, spanning from today out to about 12 billion years in the past. Each of these insets illustrate the BAO feature that we observe in each case. And you see that we detect that feature extremely nicely at high significance. The aggregated precision that we've obtained with DESI is of the order of 0.5% on this BAO measurement, which is also exceeding the precision that we had so far with SDSS of about 0.6%. Instead of combining them into an isotropic measurement, we can also determine individually what we can say on omega m, so the density of matter, and the product of the Hubble scale today, H0, times the size of the BAO feature, RD. And this is what is shown on the right-hand side, again, for the various tracers that we have. There are 2 things to notice from this plot. First of all the tracers are in very good agreement with one another. So we have excellent consistency across the DESI data. But the other interesting feature of this plot is that as a function of redshift, we see that the degeneracy angle between these 2 parameters that we determine actually rotates with redshift, which means that by combining the information obtained from all our tracers, we're actually able to constrain much more tightly both of these parameters, omega m and H0 RD. And this is what is shown with the central black ellipse at the center of this plot. So going beyond omega m and H0 RD, what can we say? Let's start with H0, so the expansion rate of the universe today. This is a topic of particular interest because of a pretty long controversy that we've now have in cosmology between 2 approaches for the determination of H0. On the one hand, we can determine H0 from the late time universe using a distance ladder approach, where we use type 1a supernovae to study the expansion rate of the universe, themselves calibrated through pulsating stars or Cepheids, themselves calibrated for the most nearby one through parallax effect, which is a direct determination of the distance of objects. And so we have a local determination of H0, which gives a value of about 73 kilometers per second and per megaparsec for H0. On the other hand, we can also determine H0 from cosmological studies of the early universe, and in particular through the study of the cosmic microwave background. And this leads to a much lower value of H0 of about 67.4 kilometers per second and per megaparsec. And given the very tiny error bars of these 2 measurements, there's a discrepancy at about a 5 sigma level between these 2 determinations. So what can DESI say about this H0 issue? Well, as I mentioned, DESI only is sensitive to dimensionless quantities, not directly to H0, but to the product of H0 times RD. However, RD, the size of the BAO feature, can be determined from first principles. As I mentioned, it's just the product of a time the sound speed. And the sound speed is directly related to the density of baryons in the early universe, which can be determined by the study of Big Bang nucleosynthesis. And so using the information from Big Bang nucleosynthesis, we can determine omega b and therefore the size of our BAO feature. And therefore, that allows us to break the degeneracy between H0 and RD and have a 1% measurement of H0 from DESI and Big Bang nucleosynthesis. We see on the right-hand side the value that we obtain from DESI in blue, which is about 1 sigma larger than the value we obtained from cosmic microwave background, so in pretty good agreement with the CMB. However, it's still 3.7 sigma away from the value determined from the local universe approach with the Shoes experiment. Let me now turn to dark energy, which is really what DESI has been set out to study. So first of all, as I mentioned, DESI is the dark energy is studied through its equation of state, so the relation W between pressure and density. It's a very hard measurement. I'm illustrating here the change that we expect on the 2 distances that we measure for almost a 15% change in W. And you see that the change in the distances that we measure is only of about 2% for a 15% change in W. So it's a very hard measurement. studying W in the case where we assume that W is constant also allows to to have some results on the cosmological constant hypothesis, because if the answer to the accelerated universe is a cosmological constant, then we expect W to be rigorously equal to -1 at all times. So under this assumption of a constant equation of state, DESI has a 15% determination of W, which can be strengthened significantly by combining the data from DESI with early universe data from cosmic microwave background and late time universe from type 1a supernovae. And we then obtain a 2.5 measurement of W, which is totally compatible with W equals -1 in the hypothesis of a constant equation of state. So no change in time. However, DESI has a lot of spectra, as I said, and the constraining power of DESI is such that we can allow W to vary with time. And so this is the simple equation that we're assuming for W with the linear evolution as a function of the scale factor A of the universe. So the scale factor is related to redshift as A is 1/1 plus Z. A equals 0 is the Big Bang, A equals 1 is today. And so you see that with the simple parameterization of the equation of state, today we would have a W equal to W0 for A equals 1. What you have to notice with the plot on the right-hand side is that clearly by combining DESI, CMB, and supernovae, we see a deviation from what we would prefer in the case of a lambda CDM standard model, which would correspond to W0 equals -1 and no evolution, so WA equals 0. We clearly see that whatever the supernova sample that we're using, all three of them show a deviation from lambda CDM. And going back to the plot that I was illustrating before of this isotropic distance measurement as a function of redshift, I'm now, in addition to having this line at rigorously 1, which would be the case for a lambda CDM model, I've also added the best fit value, which is that dashed line corresponding to our preferred model with a varying dark energy. And you see that it does fit the various points that we have as a function of redshift better than a lambda CDM model. So is dark energy weakening? Let's try to understand what that means. This is illustrated in this plot here. What this shows is the change of the scale factor. So the rate of change of the scale factor. So the expansion of the universe as a function of redshift. So redshift increases to the right, which means that time increases to the left. And what we see are two curves here. The red dashed curve is the prediction for this expansion rate for lambda CDM model, so cosmological constant, whereas the green band illustrates a preferred model with the dynamic dark energy. And so if we start from the right-hand side, so for the earlier epochs in the history of the universe, in both cases, we start out with a long period of deceleration while the universe is still dominated by the matter in the universe. But then matter dilutes, dark energy to first order stays constant in terms of density, so takes over. And in the recent universe of starting with redshift about 0.7 out to today, so starting 7 billion years ago and out to today, we have this phase of accelerated expansion that was discovered with the type 1a supernovae. But in the most recent universe, in the last billion year, you notice that the best fit model from the DESI data does not follow what would be predicted with the lambda CDM model. The acceleration is not as strong, and we could possibly even have a turnover of this A dot factor in the most recent times. So the acceleration with the preferred model fitting the DESI data is slower than what we would predict with a lambda CDM model. Now, is modified gravity the explanation to what we're seeing? We can also provide an answer to this question, given that DESI is studying clustering on all scales, as I've mentioned. And so in that case, what we're doing is using the Poisson equations that govern the trajectory of particles. We have two equations, one which translates this trajectories for massive particles, such as galaxies, and this is what DESI can constrain. And we have another equation which constrains the motion of massless particles, such as light, to which DESI is not sensitive, but other probes are. And so what we do to test for modified gravity is to consider that the two potentials, psi and phi, could be different, not necessarily the same, unlike in general relativity. And we add two parameters, mu and sigma, that are allowed to vary with modified gravity models, even though in general relativity, these two parameters would be equal to 0. And what we constrain is the values of these two parameters today, mu naught and sigma naught. And this is illustrated in the plot that you have here. DESI, as I mentioned, is only sensitive to the trajectories of massive particles, so only can constrain mu naught. And this is clearly visible in this plot here. The DESI constraint is the green band, which is only sensitive to mu naught. But what you have to see is that DESI is totally compatible with mu naught equals 0, meaning that there's no indication of the need for modified gravity, given the results that DESI has obtained so far. We can also have a constraint on sigma naught by combining with additional data sets, such as the lensing of the cosmic microwave background, for instance. And in that case, we can constrain both mu naught and sigma naught. And once again, you see that there's no indication within 1 sigma. This is compatible with general relativity and no indication of a need for modified gravity. Finally, I want to say one word about what DESI can say on neutrino masses. DESI by itself is not sensitive to the masses of neutrinos, but is sensitive to them through a constraint on the matter density in the cosmological model, and similarly through the measurement of H naught. And so it can help using the results from the DESI analysis. We can actually constrain the sum of the neutrino masses by raising the degeneracies that are intrinsic to the studies of the cosmic microwave background on this topic. And this is what illustrated on the right-hand side. You have the blue and orange ellipses, which are the constraints on the sum of the neutrino masses coming from the cosmic microwave background as a function of H naught. And because DESI can constrain H naught, we can lift those degeneracies and provide a much tighter constraint on the sum of the neutrino masses. So in the context of lambda CDM, we provide an upper band on the sum of the masses of 0.08 electron volt, which we can tighten further to 0.7 electron volt by adding the information coming from clustering on all scales. But these two limits are in the context of lambda CDM. And given that DESI seems to prefer a model with dynamic dark energy, we're also showing the constraint in this context. And then we have two things. Not only is the upper bound significantly looser because we're having additional free parameters in this fit, but we also notice a shift towards a best fit into the positive regime for neutrino masses, which is actually quite satisfactory, given that in the lambda CDM model, we see that the best fit for neutrino masses is actually in the unphysical regime where the neutrino masses would have to be negative. So this is still first indications coming from DESI. This is only based on the first year of DESI data, but these are already very interesting bounds given the terrestrial lower limit on the sum of the neutrino masses of close to 0.06 electron volt, which are coming very close to the upper bounds that we're having from cosmology. And so this is really what I wanted to show today about the dark energy spectroscopic instrument and its status. The animation you have on the left-hand side is the actual 3D map of our galaxy. If you were just traveling through the universe, sorry, I said galaxy, I meant universe. If you were traveling through the universe, you could actually see this as clustering. This is the real 3D map that we've measured and on which we've put the images of the galaxies. And I want to highlight that all the results that I've shown so far are only based on the first year of data. And these results are statistics limited, which means that by continuing to use the new observations from DESI, we can actually constrain all these parameters that I've talked about much more tightly. And this afternoon, we're releasing the first results from the 3-year study of the BAO information from DESI. And so I strongly encourage you once more to attend this special session that we're having this afternoon, where the new results will be presented, this time based on 3 years of DESI data. And just as a teaser, the animation that I'm showing here is the actual map of the universe with 3D data coming from that 3-year measurement of DESI. Each of these points are real galaxies that we have in our universe, and which you can see in this map here. Thank you for your attention.
Okay, we have time for questions. Please go to the microphone.
Hey, David.
Yeah.
I'm over here
Okay.
on the other side. Look this way.
Oh, right. Go ahead. Sorry about that. Please ask your question.
Okay. Great talk, Natalie. Thank you.
Hi, Josh.
Just a sort of a comment and a question. You highlighted the Hubble tension between CMB and BAO on one side and shoes on the other. Of course, there are other measurements of H0 using the local distance ladder, in particular the Carnegie Chicago team, which is finding a value sort of intermediate between the two, around 69. So I'm wondering if you could just comment on consistency between the DESI results and the some of the other local measurements of H0.
Right. So thank you for this comment. What I want to comment on is that indeed we prefer a value of H0 that is pretty low. Nevertheless, being low, it's slightly higher than that of the CMB. And there's an interesting article that was published a few weeks ago, a month ago, that studied the values of H0 that would be determined from various probes if the real universe was indeed following a dynamic dark energy, but was studied in the context of lambda CDM. And what this article shows is that in that case, you would misinterpret the value of H0 and you would obtain different values for the CMB, for BAO studies, and for type 1a supernovae that actually follow the trend that we're observing today. So maybe not to the excess of the shoes values that I'm showing here, but indeed compatible with other approaches of the local determination of H0. And we would indeed observe different values of H0 following what we're observing today based on this misinterpretation of the data in the context of lambda CDM, if the true universe is indeed following a dark energy, dynamic dark energy component. So I agree that shoes is extreme. There are other determinations that are closer, and then that could be interpreted in the context of dynamic dark energy pretty nicely, actually. Tang and Brout and others in 2024.
Okay, on my right.
Hi, thank you for the talk. I was curious, you showed the footprint for DR1, and I was curious what was the rationale behind like where you were targeting for this first year of data?
Okay.
So we started out by aiming at the galactic plane, and the main reason for that is that there are a lot of data in this region, and that allowed us to have the most coming out of this first year data by combining with other data sets. You actually see that there's also a slight excess of data around and the declination of 30. That is not on purpose. That is just because when there's a lot of wind that enters the telescope, we have to avoid the wind. And that's the area that we covered when the wind was too high. But mostly the aim was to cover the galactic plane to take advantage of the additional data sets that are in this region.
Thank you.
Okay, we have a question from the chat from Alec Peck, who asked, does the downturn to deceleration for variable W in recent times imply that the model would leave the dark energy dominated era?
So not yet, really. So what we see basically is W that is not -1, but slightly larger, so closer to 0 in the recent epochs. That is still a regime in which dark energy is totally dominating. However, if we want to extrapolate for the distant future, well, actually, I should not even have said that, because the future is totally unpredictable, but the equation of state model that we're using only allows a linear evolution with scale factor. So indeed, that means that in the distant future, W would get closer and closer to zero. And so it would mean that dark energy would behave more and more like matter, actually. So we could have a turnover and then like a universe basically fully made of matter. But this really depends on the model that we have of the equation of state. And so I think that we should not extrapolate that far. What we can say is that today, dark energy seems to be weaker than we would expect with the cosmological constant, but we're still totally dark energy dominated.
Thank you. Let's see, on the left. Yeah, go ahead.
Could you give a Z value for the maximum dynamic dark energy density?
What do you mean by maximum?
Well, it reaches a maximum and
no, that really depends on the modelization that you're using for the equation of state. So far we've used this linear model, W naught and WA. We've started testing, and Josh actually has provided a very nice article testing other models that are more physically motivated. So far, we have no model that fits the data much better than this simple equation of state. So I think that there's a lot more that needs to be done on the theory side to try to understand the results that we're achieving. What is currently maybe slightly discomforting is that in the past, we seem to have a dark energy that has an equation of state that is very negative, even more negative than a cosmological constant. This is not easy on the theoretical side, at least that cannot be achieved with a single scalar field. So I think this is the area where there's more investigation that needs to be happening probably.
Okay, let's thank our speaker again. And time to bring up the next speaker. Okay, so in the last talk of this session, we're going to learn about measurements of the cosmic microwave background, both with an older instrument called ACT and a brand new instrument called the Simons Observatory. Our speaker is Mark Devlin, who is the Reese W. Flower Professor of Astronomy and Astrophysics at University of Pennsylvania. He has a BA from University of Wisconsin-Madison, MS and PhD from University of California at Berkeley. And he has many different projects, including the Simons Observatory and the Atacama Cosmology Telescope, which he's going to be telling us about. In addition, he has various awards. Let's see, awards for distinguished teaching. He is a fellow of the American Physical Society, and he is a Kavli fellow and a Sloan fellow, and has held an NSF Career Award. And so let's see, Mark, can you please come up and begin your talk?
Thanks very much. So those are two tough acts to follow. So, and I especially want to thank Nathalie for setting up a lot of cosmology for me. So that's all very good. So I'm going to be talking about a couple of experiments here, the Simons Observatory and the Atacama Cosmology Telescope. These are fairly large projects which have been evolving on the Atacama Plateau in Chile over the last 20 or 30 years. We have a lot of funding sources. I especially want to call out the National Science Foundation for their continued support of our work in Chile over the since 1998. And they've really helped to bring everything along and make this possible where we are right now. So to make progress here, I'm going to have to get you to believe two things. The first is the universe started in a Big Bang. And Nathalie set that up, and that we can observe the universe today, and there's a universe out there. Nathalie also set that up. So, and the reason I want you to believe that is because in order for us to make progress, I need you to understand that the universe has to go from A to B. It has to evolve over time. and over cosmic time. And that evolution has to be dictated by how the universe works. And again, Nathalie described a couple of those things. But basically, there's a recipe. That recipe is called currently the Lambda CDM model, and that model has a lot of inputs to it. So we have a universe that begins, we have a universe that we observe today, and how it does that is going to be depending on the parameters that go into the model. So effectively, what we're going to be doing today is to learn how we go about not knowing what the universe is, but actually measuring the universe and inverting that whole problem and saying, if I can know what the universe is as a function of time, then I can invert and find out what those parameters are. In other words, to find out how the universe works. So in doing so, we can learn, things about how things are happened in the beginning. In particular, we learned about inflation. There are gravity waves from quantization of gravity in the early universe, which propagate from the first instance and then imprint themselves on the cosmic microwave background 380,000 years later. That would be super cool to measure because it tells us about the energy scale of inflation. And, that's getting access to very, very early times. We can learn about particles, neutrinos and light relics. The number of relativistic species are ineffective, can be determined from these measurements, the sum of the mass of neutrinos as well. And as we just heard about, there are things like dark energy, which determine, again, the evolution of the universe. So again, I want to repeat is that the name of the game is not just say, let's just look at the CMB and magic occurs. The name of the game is to actually examine the universe again as it evolves over cosmic time and constrain all of the things that must go in to that evolution. So I know you've seen a lot of these pictures over time. They sort of look like your cat threw up on the kitchen floor and you stirred it around a little bit. And my goal here today is to sort of demystify these maps and to teach you how we actually extract information from what looks like noise. And this is an ACT temperature map, Atacama Cosmology Telescope map. And again, as we learned, this is a snapshot of the universe at around 380,000 years after the Big Bang. And what it is, the red and blue represent temperatures, temperature fluctuations on the sky. And they also then would therefore represent density fluctuations in the early universe. So its temperature and density are related. So you see these plots a lot, and so what do they mean? And concentrate on the top one, which is the black one, which is the temperature curve, and it's basically a two-dimensional Fourier transform of that map. And your eyes are already doing the Fourier transform yourself, I hope. And you see, I pointed out that there is power on the y-axis and multipole, or really just angular scale on the x-axis, and I've marked where 1 degree is the peak in that power spectrum. And your eye can go look at that map and say, well, I can pick out where the biggest fluctuations are and their scale. And if I know that that's a degree, then you can probably figure out that map is about 10 degrees on a side, right? And of course, there's a big sky out there. This is just a little chunk of the map. So the curve that you see there is a theoretical curve, which is the Lambda CDM model of what we should be seeing when we look at the Big Bang. When we look at the cosmic microwave background. So it's a model spectra of what the Fourier transform of that map should look like. Now, what goes into that are cosmological parameters. And so again, things like the baryon density, cold dark matter, the angular scale of the horizon, where that peak is, for example, all sorts of things go into that, but they're not that many. It's a sort of a limited number of things that dictate how that curve should look. And so you can see why people wanted to measure this, right? Because if you can come up with a theoretical model that makes this curve, then if you measure the curve, then you can actually constrain those parameters. And that is very enticing to cosmologists, right? So this is why so much effort has been going into measuring to measuring that, that noisy map that you see there. So we're going to learn a lot from that. Now, I also want to point out that the temperature scale you'll see in the black curve, it's 350 microkelvin, which says that the scale of the fluctuations of that map are 350 microkelvin. Now, I know that's just a number to you, but to me as the experimentalist, I have to actually design an experiment which has a sensitivity to measure that. And remember, we live in a 300 Kelvin room here, and my telescope is on the ground. We'll show in a second. And, has to look through the atmosphere, which is, many Kelvin. It has to look through dust, has to look through all sorts of stuff. So we're trying to extract a very tiny signal on top of a DC background, or even a fluctuating background, and to get these kinds of curves. Now, those maps sort of give you the impression that the universe is static. Obviously, it's evolving, so it can't really be static. This is just sort of a simulation of what it would be like to be just before the cosmic microwave background decoupled from matter in the universe. And what it's supposed to be showing you is a sort of acoustic oscillations, these sort of oscillations that are propagating inside a causal horizon. And the causal horizon is, again, about the size of the universe when it decoupled, so about 380,000 years in radius. And these sound waves are propagating, they're moving matter, right? And it's moving around. Now, you don't get to see this because, eventually it stops, right? And the reason it stops is not because the sound waves go away, it's because the radiation has decoupled from the matter, and now we get a snapshot of what it was like. So by measuring certain aspects of this, we are actually not just measuring the density and the temperature, but we're also measuring what the velocity was, what the sound wave was doing just at that time. Super cool stuff to do, right? So you're really learning a lot about what's going on in the early universe. Now, going back to the blobby map, you have to imagine yourself as sitting there as an electron. I know you're not an electron, but imagine you were. And if you look around, you're going to be seeing hot and cold spots from these acoustic oscillations, which are producing the density, but also velocity in the system. When I observe that electron from where we are, it's going to pick up one polarization from, a temperature in that direction, another polarization from a temperature in that direction. And that anisotropy in temperature will then result in a net polarized signal being emitted from that electron as it lives in this field. That's called Thomson scattering. We all know about that from undergrad. And that's wholly predictable from the temperature spectrum. If I take a picture of the sky and temperature, I can then predict what the polarized signal would look like simply because it's just basic physics. And it produces a pattern on the sky, which is symmetric under inversion, a parity. And you then can produce the second curve on that plot, which is the green one, which is what we call the E mode polarization. It's the polarized emission from the same cosmic microwave background. You'll notice again, I put a scale on that. It's 25 microkelvin. So you might guess the first thing we did was measure the temperature, and then we made more sensitive instruments, and then we went after the polarization. But we sort of knew what the polarization was going to be because, again, it's theoretically predictable. So as we move on, we just discussed that there's gravity waves emitted produced in the very early universe. We can't see the early universe because it's behind the cosmic microwave background, but those gravity waves propagate, and it's a tensor, so it's squeezing and stretching space. And that has a similar sort of effect in the sense that if you're that electron, now you're seeing space being squeezed and expanded around you, and that also produces a polarized signal on that we can observe. Now, part of that looks just like the E mode polarization, much smaller, but another part of it looks like this, which we're going to call B modes. And those B modes are not symmetric under a parity rotation. And so they're very, very distinguishable should they exist against everything else. And that then produces the smallest curve you see there, which is actually much bigger than it actually is. We just wanted to put it on the plot. And we're going to be looking for signal levels at the tens of nanokelvin level. So every time we come up with something new to look at, it just makes it really, really hard, but also a challenge for the experimentalist like myself. So there's a lot to be learned by looking at the cosmic microwave background about how the universe is. It's just a huge amount of information encoded. So I want to take a step and pause and talk about the results that we just released yesterday for the Atacama Cosmology Telescope. It ran for 15 years. We shut it down a couple of years ago so we can do new things. And we just had our final data release, DR6. And I'm going to just briefly touch on it. Zach Atkins is in a session today. Actually, that whole session is going to be really cool. But he'll be talking about more in detail about these results. I can spend all day just staring at this movie. It's like going to TikTok and they just repeat it back and forth, back and forth. This is just this is sort of like the sum of 15 years worth of work to me. And so it's really just fun to look at. And what you're seeing is the coverage of the ACT telescope, projected on the sky or on a sphere. And it's just going to play in the background for a little bit. But and I will walk through some of it in a minute. But what I really want to concentrate on is what we can get from this map in results. And this is from the paper that's come out. Those have error bars on them, those dots, right? So this is extremely precise measurement of the temperature spectra. And again, as I pointed out, this is then used to extract parameters. For those experts in the room, we also have the polarized spectrum, the EE spectra. Again, angular scale on the x-axis, and then the power on the y-axis. Again, incredible, just precise agreement with lambda CDM. It's just so fun to watch. And then finally the TE spectra, again for the experts in the room. And you can see that the ACT telescope extends the Planck measurements out to much smaller scales, which again allows you to do finer extraction of parameters. Now, I'm not going to go through all this; is way too much to cover here. But spoiler alert: H0 attention still persists, so we didn't make it go away. And you can again look at the papers to see all the parameters that we're doing. They're listed here. They're posted on the archive yesterday. And really, we just start scratching the surface here with cosmology, but these are millimeter wave legacy surveys, and so there's lots of other things to do with them. As you know, people will take a more detailed look at these maps. So let me see. There we go. All right. So just taking a step back to what we can do with the cosmology here, again, what you're seeing on the left is the cosmic wave background in the background, and photons that are emitted from that propagating. And they have to propagate through the universe as the universe is evolving, forming large-scale structure. So this is now me switching from getting information from the CMB itself and doing the lambda CDM thing to using the CMB as a tool to probe the evolution of structure in the universe. So again, I know what the CMB is. It has to propagate past the universe. If the universe is doing something, it's going to affect what I see. And that effect is shown on the right-hand side, where you see a simulation of, again, the cosmic microwave background. And it's switching back and forth just very subtly between lensed and unlensed. So what's happening is as the photons pass by the structure, they get slightly deflected, tiny, tiny bit. And they're just going through the universe as they pass by all this stuff. And they get deflected some, tens of times. And they get deflected in the range of a couple arc minutes. Now, both those maps, we don't see the unlensed map because it got lensed, right? We can't go back and see it unlensed. So we're just seeing the lens map. So they both look like noise. So what do you do with that? Well, remember when the light was emitted, there was a horizon scale. I mean, the light could have only propagated 380,000 years. And so things inside that horizon can know about each other. They can be correlated. Things outside that horizon can't. They can't have known about each other, so they can't have been correlated unless I produce that correlation along the path. And so what you're seeing here is as they pass by all these large scale structures, get a slight correlation because of the large scale structure. From that, we can back out where and when that was happening, and then produce the evolution of the universe, basically how the universe evolved. So this offers you a really interesting thing. So you have a measurement of lambda CDM, which predicts what it should be as a function of redshift. And now you have a separate orthogonal measurement that says what it actually was. And those two things essentially agree with very high precision at this point, which is an extremely, just a great proof that we have, not proof, but I mean showing that we really understand what's going on, at least at the level right now. So, this is very exciting for cosmologists. Taking a step into a different direction here, this looks a little funny. That's the coma cluster in the optical. I obviously don't make optical measurements, and those little red things going around are electrons. And clusters of galaxies are essentially the largest gravitationally bound objects in the universe. They can have thousands of Milky Way-sized galaxies in them. And as they're sort of orbiting each other and just having this gravitational system, they strip off gas and electrons, and you have this sort of hot electron gas in the intercluster medium, and they were about 100 million degrees Kelvin. That's pretty hot. Now that whole thing emits light. And this is what this would look if you looked in the millimeter wave. That's what the coma cluster would look like. And that whole thing is embedded into the CMB. So they're sitting there, and that cluster has CMB photons coming into it from all around. And now you have these electrons in there. And what they're going to do is they're going to scatter the photons. So let me get rid of the pesky CMB and just look at one photon from the CMB. Right there. And that one photon from the CMB can go into the cluster. It can scatter off one of those electrons and then go into my telescope. But it doesn't just scatter it, it actually gains energy. So it takes that photon and it moves it from low frequency to higher frequency in the CMB. So if I observe at low frequency, I'm going to see a dearth of photons at this cluster. If I observe at a higher frequency, I'm going to see an excess. And so it's going to appear cold in CMB words if I observe it at one frequency and hot at a different frequency. So it's going to look like a hole in the sky. But CMB is 2.73 Kelvin. If there's a cluster there, it's going to look a little colder. It'll be a dot in the sky. So this, for me, and I'm interested in clusters personally, is super cool, because now I can use this map of the cosmic microwave background to search for these objects, and over a large fraction of the sky. This is the Planck data at 150 gigahertz. You add the ACT data to it, and it just sharpens up. And it's really hard for people who are not used to looking at this to really appreciate it. But you can actually see a little galaxy appear in the lower center or so. So to make this easier for you to do, I'm gonna add 3 colors to this, and in this scale, the cosmic microwave background is just gray, and that's the cloud you see there. And hot things will appear red, and cold things will appear blue. Still sort of hard to see, so I'm going to circle them for you. And you can see that we have a number of objects that we can look at. Quasars, for example. We can look at nearby galaxies, but we can also look at these galaxy clusters, which are appearing blue. Still sort of hard to deal with, so we're just going to get rid of the CMB and just look at the sources here. And again, that looks sort of noisy and so forth, but I'll point out to you, you're just going to find the dark spots, right? And all the dark spots are clusters, and all those clusters are super interesting objects. And so now we can do this, and with the new data, we have about 9,000 of those things here. And this is a plot of redshift versus the mass of the clusters. And as you might expect, as the universe evolves, they get bigger, right? Because they're merging, they're doing all sorts of things. And so that's great, but lambda CDM tells us how fast they can grow. In other words, if I go back to a redshift of 1.4 and I find one cluster that is just a little bit too massive, that could theoretically invalidate lambda CDM. And so those curves you see there are essentially those limits. And if in fact I were to find clusters that were more massive than that, then you would make lambda CDM unlikely to be exist. And you can see that this is essentially consistent with that result. That's just one thing you can do with clusters. That's fun to do with the ACT data. So let me switch to, that's old stuff. Let's go to new. This is a video that we put together, which might as well give to the Chilean Tourism Society, because because this is just a fun place to go to. And you're going to see this is now zooming into our site. I've been working there since 1998. And just everything's just been getting bigger and better. So the Simons Observatory started about 7 years ago at the same site where I had an initial experiment called TOCO, and then we put ACT there, and now we have this monster. And you can see, look at that sky; it's beautiful. It's at 17,000 feet, 5,200 meters. The pressure is about half of what it is here in this room, which makes it bad for your brain, but really good for CMB measurements. And it's also one of the driest places on the planet because it's a desert. And so we hate water, we hate oxygen, and this has very little of either of those things. So anyway, so this has worked out really well for us, and I'm just going to run you through this. So remember that I showed you this plot before. We have 3 small aperture telescopes which are probing large angular scales. They're really specifically designed to go after those B modes, and you can see where those coverages are. We have 3 of them now. We're going to add 3 more in the next couple of years. They're designed to go as small a patch of sky as we can get from this site. And so if you were at the South Pole, you could make that patch smaller. But because the Earth rotates, we have this problem that we have to we can't look through the Earth. So we've got to to change it up a little bit. And the sky coverage is shown there in the lower plot. And then we have one large aperture telescope, we call it. It's got a 6-meter diameter aperture, which covers the rest of the scale and is going to survey 40% of the sky. Turns out that the primary mirror of this telescope is the same diameter as the ACT telescope. So why did we take the ACT telescope down? Perfectly good telescope. And the reason is that this one has a secondary mirror, which is also 6 meters in diameter, which allows us to make a very, very large focal plane and pack more and more detectors into this system. So that's worked out. I'll show you pictures in a second. Now we sold this not as a cosmology experiment. We sold it as a millimeter wave legacy survey. And so, yes, it will do all the things I just described for cosmology and all the things that ACT was doing, but also because it's got a really, really high sensitivity, certainly the large telescope, it can make maps of the millimeter wave maps essentially every couple of days. And then as you do with time domain, you can just subtract them and see things change, like active galactic nuclei changing, all sorts of stuff. I'll get shown in a second. We can do extragalactic astronomy, obviously cosmology. We can look for Planet 9, and one of my favorites, looking at star formation in our own galaxy. So it's really got a lot going on with it. Just to touch bases on the time domain stuff, this is just, you might know that the Rubin Observatory is in Chile as well, and it's going to be observing essentially overlapping with the Simons Observatory. So that's an optical map. And as they both scan, they're not really scanning the same spot at the same time, but I faked it here. And but we're going to be looking at C&B maps while they're looking at in the optical, and we probably will see the same sources varying with time. That's in addition to the weak lensing science that we can also do with the cosmology. So having both these telescopes up and running at the same time is going to be great. I mean, it really is going to be a lot of fun to compare the data. Just touching base on something else that Simon Observatory will do is, we're going to be making very, very precise measurements here. And we just heard about the Hubble tension in Nathalie's talk, so I won't repeat it. But, the tension that we'll get from the CMB, if in fact the center stays the same, this is just a forecast you see there, it's going to be, undeniable. We're not talking, a couple sigma. We're talking like 8, 10 sigma tension if things persist. So that's going to put a lot of, it's going to keep us all in business, I guess, because we're going to have to figure out what that is, right? And the ACT data pretty much disfavors dark, early dark energy at this point. But there are a number of other things that we could come up with. And I'm sure the theorists will figure something out. And we'll get somewhere with this. It's going to be fun. So let me tell you about how this telescope works. This is the ACT telescope. I'm sorry, the Simons Observatory telescope. Up top, you see the CMB. Light comes in. It's a telescope, and it focuses from the primary mirror to the secondary mirror, and it goes into our rather large receiver cabin. And we built a brand new camera. It's hard to appreciate this, and I wish I could give you a whole talk on just this camera, but it's 2.5 meters in diameter and 2.5 meters long. It cools a metric ton to 4 Kelvin and 120 kilograms to less than 100 millikelvin. So just that is hard. But everything else I'm going to tell you about is even harder. So the photons go into one of 13 windows. We have 13 optics tubes in there, we call them, and they're about the size of a person. And each one of them is, again, cryogenically cooled. So it goes into each one of these windows. And an optics tube looks like that. Again, it's again person-sized, and the light traverses through a series of filters and lenses, and then ends up on a focal plane. Just to pause here, there's no way I could have built this thing, just up from scratch, right? This builds on decades of experience understanding how to do this. And remember, we're trying to measure micro Kelvin fluctuations in the presence of a 300 Kelvin telescope. So you're suppressing things by enormous amounts to get to the signal that we're doing here. And this optics tube is designed to really do that suppression, right? And to make it possible. Another way we suppress is by having multiple frequencies. And so you'll see in the chart below, I don't expect you to read it, but there are many frequencies that we look at, and that's helping us, again, take out the atmosphere, take out dust that's in the way between us and the cosmic microwave background. And then you'll see, for those of you who build these things, an impressive number of detectors. When I did my graduate work, I had 5. which I built after drinking coffee, in the lab like that, right? So now we build tens of thousands of these things. And with the help of the National Science Foundation, we're going to be building even more. And there'll be a total of 13 of these optics tubes installed over the next couple of years. So once they get down to that focal plane, it looks like this, which sort of looks like a honeycomb, but they're little horns, actually. I'm going to zoom in there, and eventually you start to see a little cross at the bottom of those. The light enters one of these horns like that, and then it ends up on what we call a transition edge, superconducting transition edge sensor, or TES. And that cross is how we get polarization. So one part picks up one polarization, the other one picks up the other polarization. And then there are actually two frequencies there in one detector. So there are really 4 detectors per horn. And then we have obviously a lot of horns, and then we have a lot of optics tubes. So there's a lot going on inside this piece of equipment. Now, the small aperture telescopes use exactly that same detector array. We just pick it up and put it in there, but it has no mirror. It just has lenses. So it looks like a sort of a large optics tube, the one I just showed you. And it's designed literally just to go and cover a big patch of the sky. It doesn't have to have a big mirror because we're not interested in those angular scales for the B-mode science. So we have, again, a receiver like the one you see there. They're plugged onto those three telescope mounts, and they've been operating for a while. So not a while, a year or so. And so I'm going to show you just what that does, just to prove that these things work. That's the diameter of the focal plane. So this thing is literally instantaneously looking at 35 degrees of sky, right? So that's a big chunk of sky, and because there's a lot of detectors there. And again, there's 3 of these things. So we've already been taking data with this. This is just to prove that it works. I don't expect you to get anything from this, but there's a temperature map and polarization maps already exist, and they're just integrating down. So, and it's going to take a long time, right? These things go for years to get to the levels that we're talking about. I just got back from Chile a few weeks ago, and I'm going down in a few days to finish it up. But the video on the right is us putting in the primary mirror. It's a long story here, but that telescope's been sitting there looking like that for about almost 2 years because the mirrors were delayed and the camera was in there for a long time. So we were all ready to go, and the mirrors finally came again earlier this year, and putting them in was a terrifying but a happy day. And they go, and that's just the primary mirror. The secondary mirror went in a few days later. And yeah, I know that we all know Mars is there. Okay, so I'm not an idiot, but when first thing you do when you turn something on is you got to look at something that you know is there. So that's a picture of Mars. And when my student Sainish Haridis made the first map, again just a few weeks ago, he put a color palette that made it red. Our PR people said you can't have it red because then they think it's an optical image, right? So now it's green. Okay, so but what you're doing with this is not so much showing that Mars is there. Again, we knew it was there. It's to prove that the instrument works, and this is just this is not even focus, right? This is just close to where it's supposed to be. And again, what I'm going down in a few days is to tune up the telescope to get it completely in focus. And then you see that we have a lot of detectors on the sky, and we're already making CMB maps. They wouldn't let me show it, but we do have them, and we have power spectrum. And to put this in perspective, I got my PhD, a long time ago, but this can do my thesis work in 1.7 seconds or so. Okay, and it can do my tenure work in about 10 minutes, right? So, so you get the idea. For a person like me who's been doing this for a long time, this is just like a candy shop, right? I mean, this is going to be great, and so it's taking data. Now, how's this going to work? This is our site from a nice drone video. You see the three small aperture telescopes in a line there. You see the large aperture telescope off to the right, and on the left-hand side, you can sort of in the center left, you can see the old ACT where we had our old telescope. The telescope's gone now, and over the next couple months, we're going to be putting in a 1 megawatt solar power plant. Which again, for me is super exciting because we dump swimming pools full of diesel into these generators, and that's going to go away very, very soon. So I'm pretty happy about that. Our friends in the UK are building 2 more small aperture telescopes going in a few months. And then our Japanese colleagues are putting another one. And I just want to point out, there's a lot of empty space there. And so we would love to see CMBS4 come in and occupy that and make this an even more productive site. And I think that's it. Thank you.
Thanks very much. We have time for questions, so please come to the microphone. Let's see, while they're doing that, let me also see if there are some questions in the chat.
There's this guy over there. I'll call you. He's over there. He's over there.
Yeah.
Hi, thank you. Wonderful talk. So I just have maybe a naive questions, but seeing one of your slides, you're saying that you can use the correlation of the CMB to explore the structures like clusters, but seems that it only prefers like a certain way redshift, like 2 to 3. Is there a reason for that?
Yeah. Yes, it prefers the peak in the gravitation in the lensing kernel is at around that redshift, around 2 or 3. So you're not measuring the structure in the local universe, for example, if that's what you're asking.
Yeah. Why doesn't it measure that?
Why doesn't it?
Yeah. Why doesn't it measure? It's supposed to be like a stacking of all these.
Yeah, I mean, I think it's just an integration. It's an integration of the line of sight distance, and so while there is still matter forming now, when you integrate that whole thing, there's less power in the local path.
Okay.
I mean, it's GR, I guess.
Okay, thank you.
Okay, on my left.
Yes, so thank you for the talk. Another naive question. What do the B modes teach us about the early universe?
Oh my, yes. So this is called it's called the tensor to scalar ratio is the big thing. So you have the tensor is a source, the stress, and the scalar is the scale what's there originally. And so we're looking at a tensor to scalar ratio of well, the limit for CMBS4 they would like to achieve is 5 times 10 to the minus 4 to put that in perspective, and the magnitude of that, if let's imagine we find it, we might not see it. Magnitude that points to essentially the energy scale that was happening in inflation, because that is from the quantization of gravity, and that tells you about that. And so that's in a nutshell. But there are a number of theoretical models which give you different levels of what it should be at. And so if it's not there, then of course rules out a lot of those things. If it is there, then you can sort of fine tune that. And then I'm sure somebody will say, well, let's find out the anisotropy in the B mode spectrum, and they'll do something, right? Somebody will figure out something which is a more expensive experiment, no doubt.
And so what is the time scale?
For what?
For measuring these B modes?
For measuring them?
Yeah.
Well, I mean, it could be, BICEP has been operating at the South Pole for a large number of years. I mean, they might find it at any time, right? And because they're just digging deeper and deeper. I think to reach the limit that you're talking about here, we're CMBS4, I think the time scale for that would be the end of next decade, right? For when they'd be done with that. We, of course, will reach a limit we predict of about 1.2 times 10 to the minus 3 in 8 years or so.
Okay, thank you very much.
Yeah.
Okay, let's see. Is there anyone on the right? Yes, please go ahead.
Thank you for the great talk. I was wondering if you could expand a little bit about why this instrument can do your PhD thesis in 1.6 seconds.
1.7. I was being generous to my PhD experiment when I said that. It might be less. Yeah, it's simply just the thing is about we can make detectors as sensitive as they can be. And what I mean by that is that the noise in these detectors is limited by the random arrival of photons that we're looking at. And so when we look through the sky, there's photons coming from the atmosphere, there's photons coming from dust, there's photons coming from the CMB. And just the noise in their random arrival is the biggest thing. So the detectors can be more sensitive than that, but there's no point in making them more sensitive because you're limited by that. When you reach that limit, since you can't make a better detector, you have to just put more detectors in. And so it's very simple for me to just say, I've got 65,000 detectors. My PhD thesis had 3 or 4, and you just divide. And those detectors were, I built them, myself, and so they sucked, right? So these detectors are even better. So it's about 1.7 seconds. I mean, it could be 1, in that level.
So I'm going to use my position as chair to ask the question. We used to hear about B modes, that there was some neutrino floor below which, when you could not, go in sensitivity. So is that still true? And if so, will you reach that sensitivity?
I'm sorry, you're saying that is the 5 times 10 to the minus 4 thing the floor?
Yeah.
I think if you go look at there's the CMBS4 white paper, which goes into the deeper discussion of this, but I think the answer is yeah, is that we can't really, you can make a more sensitive instrument, but you reach a floor about which you're going to extract any information. You can't get better than that.
Okay, and if we find no B modes at that point, what will the theoretical conclusion be?
Well, as you know, the theorists will find something else to figure out. But right now, it rules out a whole range of models. I mean, I guess is the best way of saying it. And just it'll rule all those out, and then you just have to go and make another one.
Right? Yeah, right. Okay. All right. I think we're out of time for questions, but let's thank all the speakers again, and then we're going to have some closing remarks.
Hi, I'm John Doyle. I'm president of the American Physical Society. And thank you, David. My deepest thanks to all the speakers for a fascinating and thought-provoking session. I have to say, this combination of wonder, technology, and science is unparalleled, I think, in any of the things that we see here at this conference. And it's because we're looking out in the universe. We're doing it with amazing technology. And very importantly, we can communicate this to the public in a very clear and exciting way. The questions that drive cosmology about the origins, evolution, and fundamental nature of the universe are among the most profound in science. Today's discussions have highlighted not only how far we've come in exploring these mysteries, but also how much more there is to uncover, perhaps even getting more sensitive to B modes. At APS, we recognize these discoveries as only possible through collaboration, innovation, and an unwavering curiosity about the unknown. I hope today's sessions have sparked new ideas and discussions that will continue throughout this Global Physics Summit and beyond. Thank you very much.
Okay, thank you very much for attending this session.